Exercise 7. Incorporating gravity makes things fairly complicated. Before, we could simply say we want the collision between the asteroid and the Earth without intervention to occur at a certain place and certain time, and then work backward to figure out starting positions or velocities and so forth, and then implement an intervention. In this case, finding the initial conditions at the beginning of the simulation that would guarantee a collision without intervention is more complicated. So this code is set up to actually say, well, we want the collision to happen at a certain time and certain place. And it first runs time backwards from that to determine the initial conditions, whether position or velocity, that would make that happen. Then runs time forward again with your intervention involved if you're trying to prevent the collision. So a few high points of some things in here. This is a fairly complex set of code, and there is a lot that you will have to add in. A simplifying assumption is, first of all, we assume that the Earth is simply in a circular orbit around the Sun. So as time passes, the position of the Earth is simply calculated. It's centered around the position of the Sun, and then at different times, its position relative to the Sun is given by a circle of radius equal to the distance from the Sun to the Earth, and then multiplied by a unit vector that points from the Sun to the Earth, and incorporating the angular velocity, the angular frequency of the Earth going around the Sun. And you can do the same thing for the Moon going around the Earth. Simply assume it's a circle centered on the Earth instead of the Sun. Distance from the Moon to the Earth. And then the details of this unit vector will depend on where you want the Moon to be at time zero, what phase of its orbit, so to speak. Another aspect of this is incorporating gravity. So the Sun has a position, the asteroid has a position. ClosScript knows how to do vector subtraction. So line 49 calculates the position of the asteroid relative to the Sun. So it is a vector pointing from the Sun to the asteroid. And that is a key thing we need to calculate the gravity acting on the asteroid from the Sun. Line 50 calculates the gravity field of the Sun at the asteroid. That is the force between the Sun and the asteroid divided by the mass of the asteroid. So it's calculating the field. And later, everything will get multiplied by the mass of the asteroid. What are the features here? I'll type in a couple of comments. We need a direction. Now, if you have a vector, call it A, then the norm of that vector is the unit vector. That is the vector divided by its magnitude. So its job is purely to give us a direction. So the norm of that vector simply gives us the direction from the Sun to the asteroid. And with the minus sign, that will give us the direction from the asteroid to the Sun, the direction of the gravity force, gravity field. And mag of A is the magnitude. Google Script knows how to do that. You don't have to worry about writing code to create the Pythagorean theorem. So one of the reasons this is complicated is because acting on the asteroid, we have certainly the sun. As it gets close, the Earth becomes important. And hey, there's even the moon. So in the end, the total gravity field of the asteroid is a combination of the sun, the Earth, and the moon. Okay, then we have the Kromer-Euler algorithm that was used in exercise 4. You first calculate the change of velocity of the asteroid and then use that new velocity to calculate the change of position of the asteroid. So it runs us backwards to figure out where the asteroid has to start to ensure a collision without intervention. And then it restarts and runs time forward from that. Sets up a loop for a certain amount of time. And within that loop, you will set up code similar to what you've done before, including gravity, and also including whatever intervention you're going to try. Or, first of all, do it without an intervention to see that without intervention there is a collision, to make sure the calculations are okay. And at the end, as before, it does print the minimum distance between the Earth and the asteroid. Does it hit? How much does it miss by if it misses? In this case, because everything's complex, we also have graphs of, in this case, the x-coordinate of the Earth. So that is another new element. There are 3 features involved in a graph. There's the actual plotting statement. In this case, it's going to plot time horizontally and the x-coordinate of the Earth vertically. There is this G Earth X, and that's defined earlier. So this is the 3rd element that's needed for the graph, which is the actual plotting. The first 2 elements. The second one is setting up that particular graph, that particular plot, which is the plot that's going to involve the x-coordinate of the Earth. And in this case, it is simply saying I'm going to set up a curve on a graph, and it sets up some features of that curve. Then the actual plotting of the curve gets done later at the end, as we saw. And the first element is setting up the overall graph. Now, there's a lot of details in here. Let's just summarize with a very quick, bare bones graph so you can see the most basic elements. So this just creates a graph, a template for a graph, and on that graph you can have many different plots, many different curves. And that calls it G1. Gx sets out a particular curve, a particular plot that will be on that graph. Now here I've set up some time. Time will start at 0, it will go until 10, and the time steps will be a 100th of a second. And we'll just do a simple motion. X starts at 0. Velocity in the x direction is 5. We'll just do linear motion here. Then we set up a loop. Time will go until it equals TF, which is 10. This again is the line that does the actual plot. It is GX, which is the particular curve, and then dot plot, and inside the parentheses of plot are the particular thing that you are plotting, in this case time horizontally and x vertically. Then we have the update of time and the update of position. So see what this looks like, and lo and behold, there's a graph. Let's zoom out a little. So we've got the x-coordinates the horizontal coordinates and the vertical coordinates, and you can see, well, at time 10 seconds, it reaches 50 meters if it's going 5 meters per second. So that looks okay. Very bare bones. In fact, if all you want is a simple graph and you don't want titles or a legend or anything, you don't even need the graph line. That's important if you're going to have several curves on a graph, if you want to have a title, if you want to have a legend, and so forth. But you can actually do without it. So a bare bones plot, you create a curve, and then you make plots on that curve. If you want to add more fancy stuff, you embed that in a graph. So that's the bare bones. And when you look at this code, you see there's a lot more. For instance, we don't just create a graph, we give it a bunch of different arguments. These are setting limits on the vertical axis. You can predetermine what the limits are. This is setting limits on the horizontal axis. This is giving the overall graph a title. And similarly, with the particular plot we're making, this gives it a color for the plot. And if you want a legend, if you have several plots, this will give the label in the legend for that particular plot. Now, I'll be honest, I sometimes have trouble remembering the details of how this works. So I will show you what I often end up doing is I do a search on GlowScript graph. The first hit takes you to the documentation of graphs for GlowScript or VPython. And it gives you all the details. What is a graph? What does graph mean? What does curve mean? G dots means you can display points instead of curves. You can make various types of bar plots. And this gives you all of the different labels you can create. We did not create the X label or the Y label, but you can certainly do that on the graph. And all sorts of other things that you can do. One of the things is you can have different colors. Again, if you want to know about the different colors you can do, and I sometimes forget what the basic colors are, or you can set up any color that you want. And the details GlowScript color, and it gives you all the documentation on doing that. Okay, so this exercise is more complicated than the previous ones. You have to incorporate everything from exercises 1 through 4 or 1 through 6 if you're doing momentum, and you're adding gravity, which makes the computation a little more complex and is a very good reason to use a computer instead of trying to work it out by hand. Enjoy.